Our goal is to analyze the convergence and divergence of the following series. The summation of x minus 3 to power n divided by n and start from 1 goes to infinity. What is this series? Remind yourself of the definition of a power series. A power series centered at 0 is defined as Cn x to power n starts from 0, goes to infinity, which is c sub 0 plus c sub 1x plus c sub 2x squared plus the rest of the terms. To analyze convergence and divergence of this series, we are going to use ratio test. Convergence of a power series, we use the ratio test. For the ratio test, if you have the summation of an, the limit of the absolute value of an plus 1 divided by an as n goes to infinity must be less than 1, so you have a convergent series. So in this case, our an is x minus 3 to power n divided by n. So an plus 1 is equal to x minus 3 to power n plus 1 divided by n plus 1. By ratio test, you get the limit of the absolute value of an plus 1 divided by an as n goes to infinity, which is the limit of the absolute value. Let us copy this guy down here. This is an plus 1. Now let me move this guy. We don't need it anymore. Divided by an, which is x minus 3 to power n divided by n as n goes to infinity. Now we're going to do a little bit of algebra. To simplify this fraction before we take the limit. So you end up with the limit of the absolute value. Here, if you multiply x minus 3 to power n plus 1 by n, you get n times x minus 3 to power n plus 1 divided by. Now, if you multiply these two together, you have x minus 3 to power n multiplied by n plus 1. And we are taking the limit as n goes to infinity. We can simplify this further. Why is that? Because you have x minus 3 to power n plus 1 that can be rewritten or simplified as follows. So you end up with the limit of the absolute value of n times x minus 3 to power n times x minus 3 divided by n plus 1 times x minus 3 to power n. So obviously, you can cancel out x minus 3 to power n from the numerator and the denominator. This limit must be less than 1. So you get a convergent series. Let us analyze this further. What is this limit? You can write this guy as the limit of the absolute value of n divided by n plus 1, which we know is equal to 1 times the absolute value of x minus 3. As n goes to infinity, this quantity is equal to 1. And at the same time, it must be less than 1 as well. So we end up with having 1 times absolute value of x minus 3 less than 1. What's the meaning of that? Let us go back to algebra. By using algebra, here you end up with x minus 3 more than negative 1 less than 1. So if you add 3 to all sides, you get your x bounded between two values, 2 and 4. So as long as your x is bounded between 2 and 4, you can say that the power series is convergent. But unfortunately, the ratio test doesn't give us any information about 2 and 4. We need to analyze that separately. So let us write down everything here. So far, by using the ratio test, our power series, the summation of, let's see, x minus 3 to power n divided by n, when n starts from 1 goes to infinity, is convergent as long as x is bounded between 2 and 4. But the ratio test doesn't give us any information about the bounds. What do I mean bounds? It means that when x is equal to 2 or when x is equal to 4. For these two, we have to manually check the series. For the bounds, we have to check the series ourselves. So let us begin. When x is equal to 2, our power series is converted into a regular series that you saw before. So this is your power series, am I right? Now it says, hey, my x is equal to 2. Take a look. This series becomes the summation of 2 minus 3 to power n divided by n. N starts from 1, goes to infinity, or you end up with an alternating series from what we learned before. In this class, the summation of negative 1 to power n divided by n, n starts from 1, goes to infinity. This guy is nothing but an alternating series. is an alternating series. Remind yourself of the definition of alternating series. Alternating series was defined as the summation of -1 to power n minus 1 bn, and start from 1 goes to infinity as long as bn is decreasing and bn has a limit equal to 0, we have a convergence series. So take a look. For this series, bn is equal to 1 over n, and since n is less than n plus 1, or you can take the derivative 1 over n is more than 1 over n plus 1 by algebra, you see it is decreasing. Or you could do calculus. Either is fine. F of x is equal to 1 over x. F prime of x is negative 1 over x squared, which is negative since the derivative is negative. So we say that we have a decreasing function. F prime is negative. It means that f is decreasing. So bn is decreasing. What about the limit of bn? The limit of bn as n goes to infinity is the limit of 1 over n as n goes to infinity, which indeed is equal to 0. So you have indeed a convergent series. This alternating series is convergent. The series is convergent. So we checked the left bound. Take a look. We checked the left bound, x equals to 2. What about x equals to 4? When x is equal to 4, the series becomes, so remember you have a series which is x minus 3 to power n divided by n, and starts from 1, goes to infinity. When x is equal to 4, the series becomes the series of 4 minus 3 to power n divided by n, and starts from 1, goes to infinity, which is nothing but 1 to power n divided by n, and starts from 1, goes to infinity, but 1 to power n is just 1. So you get the series of 1 divided by n, which you already know is a harmonic series, and harmonic series as a p-series is divergent. But the series of 1 divided by n starts from 1 to infinity is harmonic series, which is a special case of p-series. P-series, the summation of 1 divided by n to power p, and starts from 1, goes to infinity, and since p is equal to 1, we have a divergent series. Remember, it was by integral test. So what is our conclusion here? So for the power series, the summation of x minus 3 to power n divided by n started from 1, goes to infinity, we saw that the ratio test gives us x bounded between 2 and 4. Using the left bound, x equals to 2, we saw we have a convergent series. And when x is equal to 4, we have a divergent series. So the interval of convergence is x bounded between 2 included and 4 is not included, or you can write it as closed interval 2 to open interval 4. This is the convergence analysis for this power series, and this guy is called the interval of convergence. Let us recap what we did. We have the following power series. We want to analyze the convergence and divergence of this power series. You have x minus 3 to power n divided by n. Indeed, it's a power series centered at the origin. The terms of this power series in expanded form can be written as c sub 0 plus c sub 1x plus c sub 2x squared, and so on. To analyze the convergence or divergence of this power series, we have to apply ratio test, which says, hey, this power series is convergent if the limit of the absolute value of an plus 1 over an as n goes to infinity is less than 1. So we do a little bit of algebra. We find the limit of the absolute value of an plus 1 divided by an, and we end up with this simplified version of absolute value of x minus 3 less than 1. From algebra, x minus 3 is bounded between -1 and 1, so x is now bounded between 2 and 4. We are not done yet. Why is that? Because the ratio test doesn't give us any information about the left and right number, left bound and right bound. We have to do it manually ourselves. If x is equal to 2, then you can rewrite your power series as a regular series that you saw before. So for this regular series, you end up with an alternating series. This alternating series is basically a convergence series. Why is that? Because when we go back and check the alternating series condition for convergence, we see that Bn is decreasing and the limit of Bn as n goes to infinity is equal to 0. So we don't have any issue with the left bound. What about the right bound? When x is equal to 4, this power series converts into a regular series, which we called it a harmonic series. This is a special case of P series. When P is equal to 1, using the integral test, it is a divergent series. So we have to ignore the right bound, and the interval of convergence is including 2, excluding 4, on the left, on the right. So the interval of convergence can be written as half closed, half open interval, half closed, half open interval 2 to 4.